and I will maybe leave it for a discussion to discuss why it's a consistent map on all of GL, so on the entire algebra. But I still wanted to define the full integral over GL minus 1, G2, and then into G1. So I want to define this as integral over the 1, where 1 is a vector of just ones. Yeah, so all of them are included here. And I wanted to discuss G mu, G nu. And basically this, if we use this consistent definition, basically it means that this is, no, I don't want to go so far today. This full integral involving all of the Grassmann numbers means that G mu has to be 1. Yeah, and once I have this, I just wanted to show mg of 1, so the entire integral, and integrating here G1. I wanted to discuss that this is that of m minus 1. And mg has a natural definition that the elements of such a vector, mg of mu is basically an ordered vector of mg1, mu1. So I either take it or I don't take it, mg2, mu2, until mgl, mu-l, okay? And what I wanted to discuss is that basically you can prove this formula from what we said before. So basically you will see those formulas postulating them or just saying that this is what it is, but it actually already follows from the linearity and consistency to extend this from G1 into the entire GL space. So what we are doing here is that I took G and I transformed it into mg, and then the integral is into this transformed bunch of Grassmann numbers, and I'm integrating the full one, but they are somehow not exactly the same ones, right? So here I was writing that basically when we have an integration involving G and we are integrating G and we have all of them present, then this is 1, yeah? But now M and G are here in the integral, so it's a different map. You should view this not as an integral over some variables, but like different maps, and they have to be consistent. And now we can show that they are the same. And the way you show it is basically that we will have we will be using this formula for I was doing this here. This is the formula that we need. When the integral involves a transformed vector, it's a summation of the inverse of the matrix and the previous Grassmann integrals. Yeah. So now I have a lot of them and they are composed together. So the first one is the summation over G1 until L. Then I have m minus 1 G, and here I have the last one because I'm starting with the last integral. It's a little bit like a shell of applying them. And here I will have the integral into Gj. Then this is composed with the integral with L minus 1. So here again the same summation. Here the same matrix. Same dummy index because they are separated, and then L minus 1 and integral Gj. Nothing changes here. And this we continue until we hit the first Grassmann number. And then the game is just using linearity. G1 until L, M minus 1. And the reason why we are doing all this stuff is that later when we will be using it as a computational tool, you need to know that all the transformations that you did, they are consistent and you didn't put in something by hand, because you can produce numbers from all those calculations. That's the point. Here I have Gj and J still. This is 1. Let me maybe highlight the ones that are important. This is changing, this is changing, and this is changing, and that's defining the integrals there. And then I have G of 1. So what I achieved is that the integrals are the same. So I have a lot of integrals, and I'm integrating into Gj, and I'm integrating G1. So this is good. Yeah, the next thing is that we will need to sort those integrals. And the way you sort the integrals is by using this antisymmetry of composing those maps. And once we will start doing this, we also need to linearly expand here. Okay. So we have a summation from G1 until GL. Then we have a big product of G1 and the first one, or Elf1 if you want. Then I have M minus 1, G2, 2, until M minus 1, GL, and then L. And here I will have an integral GJ1 composed, actually GJL, sorry. The Elf1. Actually, maybe this labeling maybe doesn't make so much difference. And here J1 applied to J of identity. And now I need to do those reshufflings. And the reshufflings will be giving me two things. First of all, if I integrate into GK and I integrate GK again, so whatever function f of g I had here, after this integral, this function will not involve that integral. So I will have some, not g, some h of g, but it will not involve gk, so it will be 0. So that's the first thing that will drop, which means that all those, so from this we get that JA so J1 is different from J2, and they are all different, J3 and so on. They are all different from each other. Anytime anything repeats, we will be in trouble, and we are integrating, summing here from 1 until L, which means we are actually summing now over the permutations, so the symmetric group here. And now reshuffling the integrals is a little bit like taking JL until J1 and putting them into order 1 until L. So the sign of such a permutation is some sign of some permutation sigma. So reshuffling the integrals to be correctly reshuffled gives me sigma. Then I have M minus 1 and the inverse image of J1, comma 1 until M minus 1 inverse image of sigma JL, comma L. Sorry, I will remove this. And we are almost there, because those permutations, if we assign them correctly, will give me GL and then G1 of G1, which we said it's basically 1. So what we achieved is we got determinant of m minus 1. Yeah. So this determinant follows only from those transformation rules on the first space that we said. And then consistency means that when you have those higher order integrals, so to speak, you are just composing those maps, but to compose them, they need to anti-commute with each other. And in the end, you will have here all of them. Here there have to be all of them, and they don't have to. They are not allowed to repeat, which is restricting the sum from all possible indices to only that, and that gives us the determinant. Okay, so I think what we can still do is that I will cross out some questions, maybe in some color, and then we switch off the recording and look for some stuff. So first question is, why do we call it an integral and not a derivation? Because it's acting a little bit like a derivative, but you have nothing that reasonably integrates. The other thing I wanted to say is that there are notes from Terence Tao, and he's talking more about integrating into a differential form. So if you integrate a function from 0 to 1, you can write it as a Riemann sum, xi and then delta x, and then taking a limit. Yeah, so here we are summing, so we are integrating over some interval. But here we have those symbols here, so we are integrating a little bit into this gk, which means like we are integrating into it, so we are removing it. Yeah, and yeah. So then we went through this, and another question for the discussion is, when will we have a complete construction of Grassmann numbers? I was just sketching some ideas. So first I was defining it on this linear span of just the generators. And here I was defining this for those Grassmann numbers. Another thing that you should take care of is that basically you need to be consistent, saying what happens if I have no Grassmann number and just 5. So this should be 0, because we could view this basically as not having a Grassmann number here. So sometimes it's useful to also define this on just a number. So another question is whether we need this. And yeah, so that's something that sometimes appears in calculations. I think you don't really need this, but sometimes people want to have this. Then I was defining this GL transformation rule of Grassmann numbers, and here we made a quick computation what happens. And now if you want to say I'm integrating into those transformed ones, so in this basis we would like to be in some way covariant, and say that this is again a Kronecker delta in this way. Yeah, and then the question is, like what I showed, is this really a proof that this has to this holds for all of them? Because it's not really a proof, because I can be defining new maps which are labeled in some way by m. Yeah, so this is a little bit like what follows from what, and basically we should view the integral as a C linear map from this to complex numbers. And okay, so then another thing was that they are acting on the same linear space here, so they had to be consistent. When they have to be consistent, they have to actually be a linear combination of each other, because they are linear matrices acting or linear maps acting on the same space. Yeah, so that's why they are linear. That's nothing more than that. They are linear combinations of each other as a sum of maps. So I would say that this is roughly a proof if you assume the consistency, but I think like you have to actually postulate one of those things for defining those maps. So I think this has to be a correct definition, that for any basis of the G1 space, the integral is diagonal on this basis. Okay, and then we went on to define the full algebra, which is a complex span over all monomials that I can create. I'm writing monomials from 1 until L with some binary string that is telling me whether I take the Grassmann number or not. And then we should discuss whether we are satisfied with this extension to GL to say that now I'm defining maps. So G mu is a map from GL into GL in general. So sometimes there will be some Grassmann numbers left, and this is something I wasn't discussing so much. But anyway, this allowed us to get finally the determinant formula. So basically, this integral into all of them is basically one where when we have all of them and sorted, that's how we define it. And that's quite useful because we can then ask what happens when you integrate into the transformed Grassmann numbers. They are transformed in this sense here. Yeah, so basically it's a product of many summations, and because of those summations and the condition G squared is 0, we got this formula here. I think what we should discuss is whether everything is correct here. But I think it's correct. And one thing that will be happening later is that here we got the determinant, but often Pfaffians will appear. And here we get the determinant because one of the indices is kind of fixed, and it's fixed by the ordering of those integrals here. Okay, so okay, let me write only this final formula. I will write this formula here. G and the full Grassmann word on this, and G1 here is the determinant, and that's the equivalent of the Jacobian, which is important later. And what is also useful later is that we can just redefine everything, and you will see that M, or maybe it's easier to see if I write M minus 1G on the full vector, is also that minus 1. And in this way of writing it, you see why we have this. And this is actually an equivalent proof, but is it equivalent? So that's another question. Is this a proof? Yeah. So my point for this session is that basically those questions are not really asked, but I think it's quite important because when we start taking exponential functions of quadratic forms of Grassmann numbers, so I'm generating matrix AJK, GJGK. When we start taking those, we can form also an integral into G mu of this stuff here, and then we can ask what do we get from this, yeah, and we will be getting numbers which will have physical interpretations, yeah. So if I'm getting numbers, I have to make sure that my procedure for getting those numbers is fully consistent and not that I will have two different numbers if I do the integration in two different ways. So that's the point why I'm discussing this. Once you start using Grassmann integration for deriving some formulas, analytical formulas that you will later evaluate, you need to make sure that this formalism that we are constructing is self-consistent. Good. So finishing